thanking the organizers for this meeting and for inviting me here. It's always nice to come to Prague and to meet everybody here. So I'm going to have, this talk is about a little bit about future and futurology and thinking what can be done, and the timeline for that is quite vague, but I think that in our fields it's always good to think ahead and think about what's going to happen in the next few or 10 or more years. So the title is Science with Einstein Telescope, and I will start by describing what is the Einstein Telescope. So this is a project to construct a third generation gravitational wave detector. Why third, and what is the first and second? So the first generation detectors were the LIGO and Virgo classical configurations that have worked for more than that have worked until a few years ago and have gathered more than 1 year of data. The second generation are the currently constructed advanced LIGO and advanced Virgo that are supposed to have an increased sensitivity by a factor of up to 10 with respect to the first generation detectors, and the third generation is this future project that will hopefully take place once advanced Virgo and advanced LIGO are successful and once they have really blasted the way and started the gravitational wave astronomy, which so far is an astronomy with no sources. So the idea is to have an underground interferometer with a triangle configuration. Oops, and this is an artist conception of how it's going to look like. We'll have this triangle shaped tunnels underground, and the reason why triangle is that initially people wanted to build two interferometers with at the angle of 45 degrees, but such a concept would require drilling 4 tunnels, and these tunnels are quite long. They are supposed to be 10 kilometers long, and the cost of drilling an underground tunnel is the major component of the cost of this entire facility. So then the idea came not to build 2 interferometers at the 45-degree angle, but to build a triangle and have 3 interferometers, which will, in a sense, do the job at 75% of the cost, because you build 3 tunnels instead of 4. Why go underground? The main reason to go underground is to increase the sensitivity, especially at low frequencies. The sensitivity at low frequencies for the gravitational wave detectors is limited by the so-called seismic noise, which is the noise associated with motion of large masses in the neighborhood near the detectors. So if you move the detector underground, then you effectively shield it from all that is on top, and this low frequency noise will certainly be lower. And the pilot project for an underground observatory is the currently built Kagra interferometer in Japan, where they are in the process of constructing the tunnels, and they are planning to put an underground LIGO or advanced LIGO-like interferometer. So this is about the detector. Oops. And now about the sensitivity. So here you see a number of sensitivity or noise curves for the detectors existing and being constructed and future. This is the blue. The blue lines are the LIGO and Virgo sensitivities. These are the advanced LIGO, advanced Virgo, which is about a factor of 10 below, and then another factor of 10 below. We have the projected or planned sensitivity of the Einstein telescope. And this low frequency thing that I've told you is that you can see that the sensitivity of LIGO or Virgo really deteriorates when you go to the low frequencies. And the problem and this is associated with the seismic, this is called the seismic wall. And one of the principal goals of the Einstein telescope project is to move this seismic wall down to by a factor of 10 to to the frequency of a few hertz. So the predicted capabilities, the predicted properties of this detector are as follows. You would have the spectral range, the frequency range from roughly about 10 hertz or a few hertz to 10 kilohertz, and sensitivity strain down to a few times 10 to minus 25 per root hertz in this best range, which is the 100 to a few thousand hertz. Now, the angular resolution for the gravitational wave detectors is really poor, and locating sources is really depends on the main. If you just have the gravitational wave data, then you can locate sources in the sky by using triangulation. And in order to do triangulation, you have to have several observatories that detect the same signal. So for this project, due to financial constraints, it is only planned to build a single facility and maybe use the existing advanced LIGO, advanced Virgo as other nodes, maybe Kagra, in the triangulation. But that will essentially give the locations of sources in the sky with the accuracy of 1 to a few degrees. So this is, for astronomical standards, this is extremely poor. So the angular resolution really depends on the electromagnetic detections for the of gravitational wave events. For the long-lasting sources, for continuous sources, and you can use the fact that the Earth rotates and essentially create a network of gravitational wave detectors by combining the signal from the time when the detector moves with the Earth rotation, and essentially you create a baseline of the order of the radius of the Earth. And if this project is successful, then we may hope to build a network of such detectors, and then really have triangulation for bursting sources. And the spectral resolution will be as good as the sampling, so this will be an excellent spectral system. So what does it mean? If the sensitivity is 100 times better in terms of strain, then the range scales directly proportionally to the sensitivity, because we measure the amplitude and not the square of the amplitude of the wave. So that means that we are looking 100 times farther out than the current LIGO and Virgo, and that means that the volume is a million times larger. So 30 seconds of ET data will be equivalent to 1 year of LIGO and Virgo data. So that gives you just the scale of the potential scale of the improvement that can be achieved with such a detector. Now, given this, if we have such an instrument, what can be done? What science goals can we achieve or can we hope to achieve with such an instrument? So the principal, I think, astronomical sources of gravitational waves that we are investigating and that we hope are compact object binaries, and here I mean binaries that consist of neutron stars and black holes, or mixed black hole, double neutron stars, neutron star and black hole. Then people talk about core collapse supernovae, and here they are a natural source of gravitational waves. The only problem is that they happen quite rarely in our galaxy. Well, but the compact object binary coalescences are even more rare. There is a lot of work and hopes on detecting gravitational waves from pulsars, from rotating neutron stars. And all of these objects, if we look quite far enough, will form unresolved backgrounds. We'll have the backgrounds from these sources, and we also may have cosmological backgrounds that originate in the early universe. Now, so let me start with the coalescences. Here is the plot of the ET range for coalescences, and so this is in terms of redshift. This is the mass, and we have the two plots, the mass in the rest frame and the mass, the redshifted mass. Because the mass that will be measured from an observation of a binary coalescence will be redshifted for sources that go high in the mass. So here we have this is the range for binary neutron stars, and it's in the very low left corner of the graph. But still, you can see that they are detectable up to the luminosity distance of a few gigaparsecs, or up to a redshift of 0.5, which is quite impressive, and this is where we should get quite a number of these sources. Then, if you look at the intermediate mass black holes, which is with the mass of the order of 100 solar mass, total mass, it's you can see them from basically the entire universe up to the redshifts of reaching 10. So for these sources, you could basically trace the evolution in the merger rate, and you can see almost a significant fraction of the universe where something like this happens. So the rates, we expect that since currently our observational limit on the rates is that LIGO has seen no objects. So in the LIGO we have less than 1 per year, but which can even be 0. And so in order to get the Einstein telescope rate, you have to multiply it by 1,000,000. But if you multiply 0 by 1,000,000, you can still get a 0. But you hope that you are not actually multiplying a 0, but some smaller number. And depending on the model, you can get the rates up to hundreds per day, but that can be less, and this is quite an uncertain number. But you should have a significant number of mergers in the ET. For the large masses, you will not only see the standard stellar sources, but also the intermediate mass black holes, and that will be quite an interesting source. And for nearby sources with a very strong signal to noise, and by nearby I mean the sources within the few hundred megaparsecs around us, this very strong signal to noise will allow to measure detailed waveform, and if you have a detailed waveform, you can get quite a lot of information about what is happening with the neutron star equation of state. You can find the quasi-normal modes of black holes and do a lot of science with that. So, what sort of astrophysics can you do with the compact object binaries? You can well, if you have a lot of compact object binaries are standard sirens, so they there is a relationship that allows you to find the distance if you have the position in the sky, because the amplitude and the frequency rate of the frequency change depend on the function of mass, on the chirp mass. And if you have an independent redshift estimate, so if you have an electromagnetic counterpart, you can really do very precise cosmology, and then go to measure Hubble constant, measure the W parameter. If you have enough objects, you can measure the variation with the cosmic time. And if you have just a few sources with electromagnetic counterparts at different locations in the sky, you can also do the tests of the anisotropy of the cosmic expansion and work on the equation of state of the dark energy if you do this W parameter estimate. On the other side, if you have fixed the cosmology by other methods, and we have quite very well established measurements of the Hubble constant, you can do the star formation and compact object mass formation history in the universe, and you can do the counting of the stellar evolution, massive stellar evolution in the universe. Then, of course, with the electromagnetic counterparts, you can work on gamma ray bursts and on the mechanism, physical mechanism that leads to the gamma ray burst emission, because with gravitational waves, you would be able to probe the regions that are optically thick and unavailable for any electromagnetic observations, and that's quite a challenge. And well, counting the coalescences may lead to finding what are the real massive black holes formation scenarios, and how do we form, and how do we get these massive black holes in centers of galaxies. And I'll talk about it in a moment. And finally, with this very well defined waveforms for the nearby sources, you should get the equation of state of Richardson's matter. So here I'm showing the noise and signal from an intermediate mass black hole binary, and there is this interplay between, well, here we still have LISA, not E-LISA on this plot, because this is a field that is developing quite rapidly in changing the names and changing the designs. But you know, for the intermediate mass black holes, you could see the incoming signal in the ELISA band and predict that this is going to enter the ET band about 2 weeks later. So this is an example for a 500 and 500 solar mass binary, and then have the entire long time wave light curve and the long time waveform. So this would allow to trace the population of OLXs and you know, formation of black holes, especially massive black holes, because of if they come from coalescences. And this formation of massive black holes in galactic nuclei, if it follows through this hierarchical scenario of merging multiple black holes into larger and larger ones, then if you see these mergers, which would be, and some of them should be visible, especially for this low mass region in the far universe, then you can do the tracing of the formation of black holes in galactic nuclei and verify the scenario in which these black holes form hierarchically. Now for the neutron star equation of state, these are some example waveforms where you have a binary black hole coalescence, a numerical waveform for binary black hole coalescence, and the double neutron star coalescence. And these waveforms start at some frequency. It doesn't mean that there is no signal here. This signal is just not modeled. There is an earlier lower frequency signal that should be connected here, but this is just showing the waveform after in the merger and in the merger phase, and these waveforms do strongly depend on the masses and especially on the equations of state. So this part of the waveform, the spectrum of the coalescence, is not really accessible for the brightest sources in advanced LIGO, but for the sources seen in ET, you can differentiate between these models and do precise tests of what's really sitting inside of the neutron stars. Now, another group of issues that can be tackled with such an instrument is the fundamental physics. And for the fundamental physics, there is a number of issues that I think can be addressed. One is the question of the speed of gravity. And so if we have an event that takes place in a distant universe, and we have an electromagnetic signal and a gravitational wave signal that accompanies it, we can measure the difference in the arrival time of the two, and this difference in the arrival time may be due to the internal work and internal structure, internal mechanism of the source. For example, you have first the gravitational wave signal from a merger, and then you wait for some time until the gamma ray burst breaks out. But it can also be related to the difference in the propagation speed of gravity and electromagnetic waves. And if there is such a difference, this will be measurable if the distances are large enough, and the difference in velocity, relative difference in velocity, can be quite small. This is very similar to the studies of Lorentz invariance violation when you measure the electromagnetic signal at low and high energies, and you try to measure the constancy of the speed of light as a function of the energy. So you can use it to limit the mass of the graviton and its Compton wavelength. You can also, because that's the similar effect. And about fundamental physics, there is also these two issues that you can test the gravitational wave theory or general relativity beyond the quadrupole formula and verify how many gravitational wave polarizations there are. And this can be done by forming a null stream from the signal of 3 detectors, which should be 0, but if it's not, then there is an additional signal from the polarizations that are not predicted by the general relativity. So here is a potential possible signal limit on the Compton wavelengths of the graviton. These are the current bounds, and you can move by more than an order of magnitude with these instruments. So continuing the story about the fundamental physics with binaries is the general relativity predicts the no-hair theorem, and that means that the black holes should be described by their masses and spins and electric charges. We assume that there are no electric charges, but for a disturbed black hole that forms right after a coalescence and right after a formation of a new black hole from two incoming black holes, this will be a perturbed black hole that will radiate away its perturbations in the forms of quasi-normal modes. So if black holes are described by only these two parameters, then the frequencies and the amplitudes, the frequencies of these quasi-normal modes have to be related and have to be described only by these two parameters. So by measuring the quasi-normal modes and the decay of perturbed black holes, you can test if these multiple frequencies are really where they are. And this is a system where all of these frequencies have to be described by two numbers. If we fail to describe them by these two numbers and we see that they deviate from our predictions, then we'll see that there is something special going on and that the general relativity needs some correction, or there is a new theory needed. So this idea is called the black hole spectrography, and this will allow to test gravitational general relativity with an extreme precision. Then, if you have very precise measurements of gravitational wave strains, for example, for merging binaries, you can also test the alternative theories of gravity. And this is because in the alternative theories of gravity, there may be also dipolar terms that contribute to gravitational wave theory and the gravitational wave emission. So with the detailed measurement of the waveform, you can place bounds on this dipolar term, and in comparison with the potential bounds from advanced LIGO, this is a few orders of magnitude better. So there is quite a
lower bound or upper bound?
Well, this parameter for the omega VD this theory goes to the gravitation, general relativity if you go with this parameter to infinity. Okay, so now let me switch to another group of sources, which are the core collapse supernovae. And with the core collapse supernovae, the problem is that they are essentially weak gravitational wave emitters. So not only they are weak, they don't happen very often in our galaxy. So current estimates for the range or sensitivity of Largo Virgo, provided the model gravitational wave signals from supernovae, limit them only to the Milky Way. And in such, well, we know that the median or average rate of supernovae explosion in the Milky Way is about one every about 100 years. However, in the past 1,000 years, we have seen, or our ancestors have seen 3 such explosions. So maybe we are in a really unlucky millennium. Now there is a new millennium and we may be more lucky. But the way to go is to reach a sensitivity, and probe many more galaxies. So advanced LIGO Virgo should reach our nearest neighbor galaxy, M31, but with ET we could go to 5 or more megaparsecs. M31 lies at less than 1 megaparsecs. And here, when we go up to about a few megaparsecs, we can reach the expected rates of supernovae up to the, I wrote here up to 1 per year, maybe half per year, but there's quite an uncertainty, and there's quite an uncertainty in the strength of the signal. But this is a big step from the expected rate of 1 every 100 years to about order of the 1 per year. So we can really hope to that in the lifetime of such an instrument, we could see a core collapse supernova in gravitational waves and do all of this physics with the proton-neutron star, the shock, the accretion, formation of a black hole, or perturbation of the black hole, and the mass growth of the black hole. So, you know, these issues will be quite important. And here you can see some gravitational wave signals calculated for a supernova. This is relatively nearby at 10 kiloparsecs, and the sensitivity of these detectors. But even if we move this a factor of 10 or 100 away, you could still see some signal above the sensitivity or the noise of these detectors. And you know, if we have the signal in gravitational waves and the signal in neutrinos, we can do this trick with verifying, with measuring the time delay, and that can give a bound on neutrino mass. Well, now let me go to rotating neutron stars. And the rotating neutron stars are a subject of many studies related to gravitational waves. They will emit gravitational waves provided they are symmetric. And I always say in such lectures that all astrophysical objects that I know are in some way asymmetric. There is always some mechanisms that will want to disturb them, and especially that is true of the objects with a surface. If we can form mountains on the crust of a neutron star and support them, either by magnetic fields or by internal stresses or by any mechanism that you can think of, then these neutron stars will be emitting some gravitational waves, and it's a quite important field to look at, and there is some physics potential that can stem from that. So this is the population of known neutron stars, and these are the spin-down limits. So if we assume that the entire spin-down luminosity goes into gravitational waves, these are the strains that you would see for, I think, 1 year observation. So you see that, well, for the current detectors, there's just a few objects that, and there are these nearby quick rotators that, for which we could beat the spin-down limit, and there are some papers for Crab and for Vela pulsar where the spin-down limit has been reached. However, the ET configuration opens this field also to the classical pulsar, the slow rotators, which for which we should be able to place this spin down limits on their gravitational wave radiation. And especially interesting is this group of millisecond pulsars, which, if there is even a small asymmetry, they will emit quite a lot of, they will be very good gravitational wave emitters, and this is a population that in which they are old, but on the other hand, the asymmetry could be induced by their interaction with the companion star. So in terms of the minimum detectable ellipticity for this population of the neutron stars, you see that for the classical pulsars, this ellipticity should be quite high, but for the millisecond pulsars with very high frequencies, the ellipticities that would be detectable by ET reach, go down to the value of 10 to minus 9, 10 to minus 10, which means that we could detect mountains on neutron stars as small as 10 micrometers. And that's quite impressive to detect something that small on a star that lies a kiloparsec away from us and is the size of a city like Prague. Then for the pulsar studies, it is also very important to look at the gravitational wave signal in the catastrophic events in the pulsar history. And here you see the pulsar glitches from the Vela pulsar, which is the strongest glitcher in the sky. And these sudden changes in the period are most likely to something happening in the crust of the neutron star, and that can be associated with the gravitational wave emission. And if we have, so looking at the gravitational wave emission during a glitch should be a way to tell us what is the mechanism of the glitch, and that's the way to really look into something that is not available by in the electromagnetic domain. Finally, to finish the pulsar study, if we look in the electromagnetic spectrum, you can see various images of the sky in different wavelengths. And in this high frequency domain of gravitational waves, the image of the sky will be dominated by the collective background from the rotating neutron stars in our galaxy. And the shape of the background and its spectrum is a function determined by the interplay of the evolution of neutron stars, the period decay, the spatial velocities, asymmetry evolution or decay of the asymmetry as a function of age, or maybe the growth of the asymmetry as a function of age. We don't know that. So measuring this collective signal and getting one of these pictures of the entire population of neutron stars in the galaxy will help constrain the neutron star evolution well beyond the radio pulsar death line, and will be an important ingredient into the neutron star population studies. So now for the cosmology, I have already talked about cosmography, tracing the evolution of cosmic expansion. We can do the anisotropy studies, and we can also look at for the primordial gravitational waves and emission of gravitational waves from the early universe. So for the cosmology, here is a predicted possible measurement of the evolution of the W parameter, which describes the cosmological constant properties, and that can be done, but this requires work with other sources of information, like the electromagnetic emission. So finally, this cosmological backgrounds. This is an important ingredient into the possible science, and the stochastic background can be detected by finding the correlation between several interferometers. Even if they are collocated, but they have independent noise, then if this noise is found to be correlated, then that can be due to the background. And these backgrounds can have the isotropic backgrounds can have two components. One is the compact object background, so the coalescences of distant compact object binaries, and another is the primordial background from the early universe. So here you can see several wildly varying curves of the primordial backgrounds, and some of them will reach the gravitational wave sensitivity of the ET detectors. And the problem with detecting this is the astronomical foregrounds, that is the foreground coming from the compact object binaries that we know that there are in the universe, and that we know that they will, the collective signal of multiple faraway coalescences can be quite strong. So the main problem in detecting this primordial backgrounds is that you have to subtract these foregrounds, and that may be a problem. And I think that this will be the main obstacle in looking into this gravitational background from the early universe. So here I have a slide, general slide on how you can probe the early universe with, here is the cosmic microwave background, but then there are some gravitational wave potential probes of the backgrounds, and this doesn't really show the potential impact of the discovery of, if confirmed, of the BICEP2 circular polarization in the cosmic microwave background, which would correspond to about this these scales. So let me put the summary here of the potential astrophysics, fundamental physics, and cosmology issues with ET. And I will also say that this is all summarized in a document on the ET website that was compiled about 2 years ago, and that's the ET design study document, which contains a huge section on science with ET, apart from a lot of engineering and technical studies. Thank you.